All right, hello again. We want to begin looking at some new material this week, actually solving some differential equations. Last week we talked about if identifying and classifying differential equations. We talked about verifying if things were solutions to those or not. So we want to look now at our first method for solving those, which is known as separable equations. So with separable, what that actually means is I want to get all of the x's and dx's on the side. I want to get all the y's and dy's on the side. And then what I ultimately want to do is to integrate both sides of those equations. And typically it becomes a pretty nice problem to be able to work. Some of the integration rules, I won't lie, are might be a little more challenging here. So if you just get stuck, then go to the worked out solutions and check those. But for the most part, see if you can separate, and then I'll help you do the integration if we need to. So let's look together at number 2. Number 2, I've got x dy dx and equal to 1 over y cubed. So again, we believe this is separable. We were told it was. So I should be able to get this y cubed term and dy term on the same side. I should be able to get x's and dx's on the same side. So it looks like maybe the most direct thing to do is just to get rid of this dy term. In fact, I can get rid of that by multiplying both sides by 1 over dy. And so those dy terms go away, and I'm left with x over dx equal to 1 over y cubed dy. So I have managed to separate the problem. The only issue now is I don't have an integration rule for this kind of stuff with a y or a dy in the denominator. Bear with me one moment. Let me zoom in. I was trying to decide why I can't see everything. All right. So what I can do, though, since I've got a fraction equal to a fraction, we'll just take the reciprocal of both sides. So I now have dx over x equal to y cubed dy. And so I have integration rules for all of that. And let's do that. Let's take the integration, or integrate on both sides. So this is a Cal 2 rule, isn't it? du over u integrates into the natural log. And you may remember from your work with natural logs, we really need absolute value unless we have a good reason to not have absolute value. And then if I integrate y cubed, I'm left with 1/4 y to the 4th plus the constant of integration. All right, so I want to talk about a couple of things that we can do here to simplify this. We've essentially solved the differential equation. Since y is my dependent variable, and I know that because it's in the numerator from last week, it's kind of sort of nice if I could get y sort of kind of by itself. And again, we get into a little bit of gray area here as to what's a valid answer. Please know on your test, I'll give you credit for any correct valid answer. But let me get rid of this 1/4 by multiplying both sides by 4. So this becomes 4 times the natural log of x equal to y to the 4th. And then this is a little trick that's going to drive some of you insane. A constant times 4 is not really 4c. It is 4c, but I'm going to write that as still yet another constant. I'm going to pull that trick lots and lots of times. So go ahead and get your head around that. A constant plus a constant is a constant. A constant times a constant is a constant. There's lots of liberties that I can take there. But now what I can do is I can use my properties of logarithms and put that 4 back as a power. So, and I'm running out of room there. This is kind of sort of worked out for you on your handout. I'm left with the natural log of x to the 4th equal to y to the 4th plus c. All right. Notice I dropped absolute value. Remember what I just said is that we need to leave it as long until we have a good reason for it not to be. And so I know that any real number to an even power is positive, so I've kind of can take care of that. All right, so I'm going to flip-flop things around. I'm ultimately trying to get this sort of kind of in terms of y. So if I move this c to the other side, and then I'm just flipping sides with both things. All right, so that is that. This is this. This to the other side is still a constant. Don't let that hurt your feelings. Don't let that drive you insane. And I want to show you about a couple of other little tricks that I can pull here. If I want to get rid of this logarithm, what I can do is exponentiate both sides. So I have e to the y to the fourth power. And then from your work in calculus, you should remember that e and natural log cancel each other out. Well, let me back up. They do cancel themselves out, but I'm not so sure about this plus c business in here, because that's not in the logarithm, is it? So let me pull one other little trick. When I am adding powers, that's the same thing as multiplying like bases. Right, so let me go backwards with it. If I'm multiplying like bases, we add their exponents, and here they are added. I'm just kind of reversing that, because this e to a constant, guess what, is still a constant. And now e and natural log will cancel themselves out. So here is a correct version of that answer. E to the y to the fourth equal to cx to the fourth. I'm going to pull that little trick on some other problems later on, is why I want you to see that. I'll be honest with you, I think I did it that way on your homework, or your corrected solutions, completed solutions rather. I'll take any combination of correct answers there. Okay, so the trick is we want to separate all of these. Don't let the separating hurt your feelings too much. Okay. All right, let's look at another one. Let's look at number 6. So I've got dv dx. V is my dependent variable. X is my independent variable. And again, I want to get all the x's together and all the v's together. So it looks like, again, I didn't realize this was so close to number 2. Looks like I can multiply both sides by 1 over dv. And so I'm left with x over dx equal to 1 minus 4v squared over 3v dv. But the same thing is happening that happened a moment ago. I need to take the reciprocal of both sides. We don't have an integration rule for dv's and dx's in the denominator. All right, so that's the same problem, just flipped over. So that was easily separated. I'm going to leave that for you to solve. This, I think, is going to become a du over u case. So just consider that as you work. Number 4, again, trying to get x's and dx's together, t's and dt's together. So I can get rid of this x and get it on this side by multiplying both sides by an x. Oh, I got ahead of myself, actually. Look at what's going on down here. Let me start over. I just now realized that denominator has an x e to the t plus 2x term. So I'm going to pull the trick that I pulled just a moment ago. That denominator can be written as x times e to the t times e to the 2x. So as I clean that up, I need to get rid of both x and e to the 2x to the other side. So again, I'll multiply by x e to the 2x to both sides. That'll cancel this and this with both of these. And I need to get rid of this dt, so I'll multiply both sides by a dt term. Let's see, let me see if I can squeeze it in over here. All right, so I'm left with x e to the 2x dx equal t over e to the t dt. So I've got all the x's and dx terms together. I've got all the t's and dt terms together. I now need to finish integrate both sides of this problem. All right, and I didn't finish this on your completed section. I've noticed this is going to be an integration by parts problem. So I'll post a solution to that. All right, so I don't know, again, your calculus background, but you've got just a ton of formulas in your bag of tricks that you need to be able to pull from and get to these answers. And integration by parts is one of those. So I'm gonna leave that for you to finish. I didn't finish it on your completed ones, but I'll do that for you. The only trick you're gonna have on these are your these integration rules. I don't think you'll have any issue getting anything separated. Some of the integration is more challenging than the others. I won't pretend it's not, so just be conscious of that. Number 7 on the back, on the second page, was a lengthy problem. It took me a whole page to solve it. See if you can separate it. Number 8 works pretty straightforward, so I'll leave those for you to try. And then we did some initial value problems, I think, in the previous material. Let me look back and be sure of that. We have not done some integration initial value problems, so let's do that right now. Let's look at number 9. Yeah, all of these are that's left are an initial value. So again, this problem is really, let me find my marker. Bear with me for one moment, please. And I'm not even seeing any of my markers. My office is a mess. This problem is the same as dy dx equal to x cubed times 1 minus y. So I used y prime here. That's fine. It's just a different notation. You might prefer this notation to get everything organized. So I need this dx over here with this x cubed. And I need this off of that side. So I'm left with dy over 1 minus y equal to x cubed dx. So again, I've been able to separate it. This right-hand side integrates really nice. The left-hand side, from calculus, anytime we see a fraction, there's a couple of things you want to pull from your mind. I'm going to look for a du over u case. Excuse me. So if I choose u to be 1 minus y, then my du is a negative dy, so a negative in, a negative out. So that integrates into a negative natural log 1 minus y equal to 1/4 x to the 4th plus c. And I think at this point we can put that negative back. I think I'll go ahead and make use of this initial condition. So this initial condition says whenever x is 0, y is 3. So everywhere I see an x, I'm going to put in a 0. Everywhere I see a y, I'm going to put in a 3. And so again, this is an instance where absolute value becomes important to me. That's the natural log of -2, which is +2. This whole term goes to 0. And I'm going to pull one other little trick. That's like a -1 sitting there. So this is the same as 2 to the -1, which is a half. Now, I don't know what the value of the natural log of a half is. My calculator does. It's not even necessary. I'm going to go back and make that substitution back into this box. And here is my answer. There's probably some cleanup we can do there. I'm going to leave it and move on. Number 10 has got a cosine function, and when x is pi, y is 0 piece. Sorry, you can't see that, can you? Don't let that intimidate you. It actually, the integration works out pretty nice. On the last page, and again, I've worked out these solutions. So the trick is, can we get them separated? This is all on Canvas. Don't let the integration, all that intimidate you. You are familiar with all of those rules. So for lecture 3, we want to finish separating 1, 3, 5, and then try 7 and 8. Again, it was 7, I believe. Glance back and see. Yeah, 7. I posted solutions there. It actually requires partial fractions, which is a technique you learn in Cal 2, or you should have learned in Cal 2. Don't stress that too much, okay? Do your best on that. Get it separated, and then I've posted the integration for you on completed solutions to each of those. All right, as always, I haven't heard from any of you yet. Maybe everything's wonderful, but as always, if you have any issues, please, please, please get with me and let's talk about them.